Welcome back. This is our lecture number 28, and I am fortunate to have two of ISC students sitting in the lecture to keep me on my toes. These are students who are actually taking my current class on campus, which is more or less a replica of the class that I am taping here. So, today we are going to do a maximum likelihood code symbol decoding of the convolutional code, which is a subject that we started in the last towards the end of the last lecture. So, let me begin by recapping. So, the first thing we did last time was to formalize the final step in implementing the GDL. Remember that the steps were that you first identify what the local domains and kernels are, and then you attempt to organize the local domains into a junction tree, and assuming that that has happened, then you pass messages along the junction tree. Now, in the single vertex case, you orient all the edges towards the node whose objective function you want to compute, and then you pass messages. Okay. More generally, if you want to compute multiple objective functions, then you can think of almost any sequence of message passings you want. The only thing is that a node is ready to compute its objective function only when it has heard from directly or indirectly from every other node in the graph. Okay. So, then in the beginning of the lecture we talked about the last step in implementing the GDL, which is computing the objective function at a single node. Okay. And maybe I will just quickly show you the expression on that one. So, that expression is exactly this. So, this is the expression that we had there for computing objective function. Basically, it is just simply computing the product of all the incoming messages together with the local kernel. There is no marginalization required at this stage. Then after that we turned our attention to, so this was an example where we computed the objective function for the node x4, and based on that we made a decision, and this was an instance of maximum likelihood code symbol decoding. Then after that we turned our attention to maximum likelihood code word decoding of the 742, and we said, well, if you think about it, the only change is that you are replacing the summation sign by the maximum. So, whenever you have an opportunity to marginalize in implementing the GDL in passing messages, then instead of marginalizing by summing, you marginalize using the max operator. Other than that, there is no difference, and in fact the computations are simple, because you only do comparisons and multiplications and term by term multiplications. So, we did that, and we computed, we solved again the single vertex problem for the 742 decoding of the code symbol x4, but this is easily extended to decoding the other symbols as well. Then towards the end of the last lecture I started talking, and I give you a reference, started talking about the complexity of implementing the GDL, and you can show that the complexity of implementing the single vertex version, that is of implementing the GDL when you want to compute the objective function at a single node, is given by this expression. For the case when you have multiple nodes, it is more complicated. When you want to compute the objective function at multiple nodes, it is more complicated, but on the other hand the good news is that you can upper bound this by just 4 times the single vertex complexity. Then we turned our attention to maximum likelihood decoding of a convolutional code, but we will go through this again today. Then so we did an example here, decoding the 742. We employed maximum likelihood code symbol decoding. Then after that we looked at the problem of maximum likelihood code word decoding. Of the 742 code. We looked at complexity as measured by number of additions and multiplications, or at least the number of operations, because The operations could be addition and multiplication, but they could also be taking the max and multiplication. So, I will just say complexity in terms of the number of operations needed. So, complexity of implementing the GDL, and we gave an exact count for the single vertex case. And the multiple, actually we gave a second estimate for the all vertex case. And then finally, we look at maximum likelihood code symbol of a decoding of a convolutional code, but here I thought let us just take a quick look at that all over again. So, I will not repeat that. So, with the convolutional code, we know that basically and I am taking a very short block length convolutional code. So, there are, in this case, there are 4 message symbols. This is the state sequence through which the convolutional code encoder is driven, and this is your output sequence. Now, although I have written y0, in general y0 is an n tuple. For example, if you are looking at a rate 1 by n convolutional code, each y0 is a string of n binary symbols, but we will not get into that. That is getting into too much detail, and that might clutter up the main concept. Okay. And a similar story holds for the symbols u0. For the present, let us just assume that this is a rate 1 by n code, so that these are binary symbols. If you like, you can keep in mind the convolutional code that we developed, that we introduced right at the beginning. Let us see if I can pull that up quickly. So, if you like, you can think about this particular convolutional code where there is one input sequence and then there are 2 output sequences. Okay. And the state sequence that we are referring to is this state sequence, that is the convolutional code. As the message symbols keep coming in, it steps from one state to another. Okay. But we prefer to think of it in terms of a trellis. Okay. So, like this, except that our representation of the trellis is more abstract. Here we put down every possible state, there we just assign a variable and leave it at that. So, at the kth time instance, it is in state sk. Here we spell out all the states, there we do not. So, that is the difference. So, then the maximum likelihood code symbol decoding needs to compute this particular objective function. So, we actually write this down, and from this it becomes apparent that we have an MPF problem. Okay. And in fact, in an earlier lecture we did put down the local domains and kernels. So, let me carry those over here. Okay, so these, for this particular problem, these were the local domains and the local kernels, and now the question is how do you organize these into a junction tree. So, there are 4 of these, I ranging between 0 and 3, there is 1 here, and again here the I value ranges from 0 to 3 in these cases. So, in all we have 13 states, and so that means that okay, so I have some juggling of space to do to fit all of this, but so let us try to organize these into a junction tree. So, it does not really matter where you start. I will start with the state as 0, and now you look at these local domains and say what should I connect to, and we are going to use Prim's greedy algorithm. So, we pick a node which has maximum intersection with this, and for example there is one which is S. So, from here you see there is an S0 U0. So, you pick that. So, that has intersection 1, edge weight 1, and then you see that you can tag on U0 here, and I am going to do this rather quickly because we have quite a bit of ground to cover, and you have already seen how to construct a junction tree earlier. Okay. So, next I am going to pick S1, S0, U0, and that is forced because there is an intersection of 2 here, that would give me an edge weight of 2, and then I have some so I am looking for something that has an S1, and I see that I can have an S1 U1. So, I am going to connect it to that. I could also connect it yeah. So, this is right, as I said I am not going to dwell on this, you can figure this out on your own. So, this will then be S1 U1 and then U1. And then you have S2 S1 U1, which you can connect to this. Then you have S1 U1, S2 U2, to which you can connect U2. And similarly, now you would have S3 S2 U2, which leads to S2 U2, and you can connect U2 here. Sorry, this is not S2 U2, this would be S3 U3, S3 U3 and U3. So, let us see, I have got I should have 13, I have 3, 6, 9, 12. Okay, so we are doing good. So the last state here is then S4, S3, U3. So this is your junction tree in this case. Okay. And you can verify that if you look at the edge weights, the sum of the, if you use the test, compare the node weight and the edge weight, you will actually find that the difference is equal to the number of variables. So this is the junction tree. You could also verify it by projecting onto each of the variables and checking that you get a tree. For example, if you project onto U1, you will get these 3 nodes. If you project onto U0, you get these 3, and so on. If you project onto S2, you get these 3. So it is always a tree when you project, and therefore this is a junction tree. So now let us consider single vertex. Well, our problem is single vertex in nature, because we are interested in computing P of UK, and well, in general it is not, you want to compute it for all the message symbols, but let me just assume that what we are interested in is in just maximum likelihood code symbol decoding of UK, where k is 2. Okay, so in all of this, let us assume that k is 2 there. Then what you do is you, as we mentioned earlier, you would orient all the edges towards node U2 and pass messages. So let us actually do that. Okay, so now you have oriented it all towards this, and perhaps we will just circle this in red to indicate that that is the objective function of interest. And now you are going to pass messages, and so the schedule is quite so in this direction messages are flowing like this, and here they are flowing like this. All right. Let us just see what kind of messages will flow in this along this graph. Now I want to also indicate where it is we have the marginalizations taking place. So for example, here in going from here to here, it is an injection. So the first marginalization actually takes place here. So let us indicate that with let us put a dotted line. So that is your first marginalization, and what you are going to do here is you are going to marginalize by summing over S0 and U0. So remember, the junction tree requires that you pass messages, and the messages that you pass are in accordance with our formula, that is, you take the product of the incoming messages and you multiply by the local kernel and then marginalize as necessary. Here no marginalization is necessary. So this is the first instance when we marginalize. The next instance when we marginalize is similarly here. So there is a marginalization that is carried out here, and this time this marginalization is over S1 U1. Now if you look and similarly in the other direction there are marginalizations, we will come to those later, So going in this direction, which sometimes is called the forward direction, what you are passing here, so the message, so you are going to multiply all these local kernels and then you are going to marginalize, but what is left is a function of S1, okay, because there is no U1 here, it is a function of S1. So let us denote that particular function by, so let us say that the function that is appearing here is F1 of S1. Let us call that F1 of S1. Now this is the function that is here, okay, that is the message that is being passed along this edge, and analogously there is a message that is passed here which is f of f2 of S2, and that is taking place here, all right. So now in this particular case we are interested in the all vertex version of the in the single vertex version of the GDL, that is we want to decode U2, but in general, since in any practical application you will want to decode all the message symbols, there's the message passing schedule that people adopt, okay, is a schedule which has the nature of a forward backward algorithm. So what they do is they go, all the messages are passed from here to here as if this were the objective function, and then messages are passed all the way back. So there is a forward and there is a backward. Here we are doing a hybrid because we are going forward up to here, and then here we are doing backward. But so that means that in the course of computing this you get to see a little bit of the forward and a little bit of the backward computation that actually is taking place. Okay. But one thing I want to point out is that once you set up the junction tree, then basically your algorithm is laid down, because now you know what messages to pass and everything is clear. The only thing is I am trying to give you some additional insight. So at this point we really are done. We have solved the problem of maximum likelihood decoding because we just do it by passing messages. By the way, the algorithm that I am teaching you now is called the BCJR algorithm for decoding convolutional codes, and it was the case some over maybe 10-15 years ago. There was a paper that appeared in the literature, a very nice paper which described this algorithm, but it carried out the algorithm somewhat in isolation, whereas here we are coming across the BCJR in a very natural way as an outcome of simply implementing the GDL on this particular message passing dictated by the GDL on this particular junction tree. Okay, so you see it comes out very naturally, and I will also mention that Viterbi decoding will also come out naturally from in this framework. Okay. So what we really are learning here is called the BCJR algorithm. So I think what I will do is I will go ahead and put that right in the title, which is where it belongs. So this is the BCJR algorithm. So the B stands for Lalit Bal. This is Cook, Jelinek and Raviv, and Lalit Bal was actually a former student, long time back student of IIT Kharagpur. All right, so here we have this. Now just to give you some insight, let us go ahead and look at what happens in between the computation of F1 S1 and F2 S2. Okay. So maybe just so that things are clear, I will write down the expression for F1 S1 right here. So F1 S1 is equal to the marginalization with respect to S naught and U naught of P of U naught P of S naught times P of y naught given S naught u naught and P of S 1 given S naught u naught. Okay. So, and I have written this, but I am actually going to port it over to the next page, okay, because we do not really want this cluttering this page. So, let us move this, well, ouch, I need to try that once more, cut and let us paste it here. Okay. So, that is the first computation, but now let us also similarly put down the computation for F2 S2. Now, we are going in this direction here. So, I want to put down the computation of F2 S2 and that will involve F1 S1 because that is the incoming message here. F2 of S2 is the marginalization with respect to S1 U1 of, well, I have F1 S1, I have P of U1, I have P of Y1 given S1 U1, P of S2 given S1 U1. Okay. So, you see that these are just simply the local kernels. See that the F1 S1 is the incoming message here, U1 is the local kernel here which becomes the message here. The local kernel at this node is precisely this and the local kernel here is this, okay, because the product of these three is the message here and then you have the local kernel as well. All right. So, again let us take it to the next page. Okay, so, we have these two expressions. All right. Okay. So, now the question is, well, I want to focus on this because in some sense this is the generic iterative step. This is the generic iterative step in the forward direction. And to see that I am going to introduce, so we'll get try to get some feel for it via the example of our code whose polynomial generator matrix was 1 plus d squared 1 plus d squared. So, if you recall here the trellis in that case okay, we have the trellis here, but perhaps that is more than we need. So, let us go back and draw it ourselves. So, in this case I just want a single section of the trellis. So, my states are going to be 0 0, 1 0, 0 1, 1 1. And now think of this as the collection of all possible states S1 and this is the collection of all possible states S2. and I am going to use our older terminology of how you go from one to the other. So, you can go with an input of 0 from there or from here. And similarly for the other states. Okay, I think I remember what I did. Since drawing a dotted line is not the easiest thing here, I am going to just choose a different color for one. Okay, so let us just choose red for a 1. Okay, so now we are done. These are all the possible transitions. And I will orient the edges in this direction because we are going forward. Okay. So, just to keep in mind, so what is going on here is that I want to illustrate the passing the message computation between here and here, and it turns out that on the trellis it is equivalent to a computation that is taking you from f1 of S1 to f. So, on this side what you come in with is a function which is f1 of S1, and then what you exit with is a function of S2. Okay, so, this is what is coming in and this is what is going out. Okay, but what is the nature of this computation? And I claim that really what is happening here is a matrix multiplication. Okay. So, let us try to make that clear, and again I am going to repeat that formula just for clarity. Okay. So, we have that formula here, and I want to first of all, so first I want to rewrite it as f2 of S2. Maybe I should choose the blue to be consistent. So, let us say that f2 of S2, and I want to treat this as a summation of S over S1 of S1 of f1 of S1, and then there is an interior summation which is over U1, which is P of U1, P of Y1 given S1 U1 times P of S2 given S1 U1. Okay. So, this multiplies this over here, and one point I want you to note is that if you look here, now P of U1 is the a priori probability of the symbol U1, and in general we assume that the message symbols are equally likely to be either 0 or 1. So, this is a half, it is a constant, so you can ignore this, it will pull right out of your computation. So, pay no more attention to this. So, you have these two terms. Now, you have a summation over U1. Now, in this summation there is a fixed value of S1, and we have in mind computing this value for another value of S2. So, in a sense S1 and S2 are fixed. S2 is fixed because you are asking for the value for a particular S2, and S1 is fixed because you are sitting inside a summation for which, and you are looking at a term for which S1 is fixed. Given the pair S1 and S2, there is exactly one message symbol. There is either one message symbol that makes the link between S1 and S2 or none, okay, because that is how our convolutional codes were, right. Because when we looked at the finite state machine of the convolutional code here, let us say that I picked S1 to be this, okay, and S2 to be this, then the only possible message symbol that can take you from here to here is this particular 0. Okay. Now, on the other hand, if I picked, let us say, S1 to be this and S2 to be this, there is no message symbol that will take me from here to here. Okay. So, in that case there is none. So, the point is that in this summation there is either one term or no term. Okay. And the other thing to keep in mind is that this function is a 0 1 function. The only values that it assumes are either 0 or 1. So, let us make a note of that. So, this is a 0 or 1 valued function. So, it is like an indicator function, and this is a constant, this is equal to 1/2. So, basically what you are saying then is that the net outcome of this entire computation is either a particular value of this or 0. Okay. And the moment you look at it like that, that this entire thing is a function of S1 and S2, and so you can if you think a little bit more about it, you can actually represent this computation as, this computation can be viewed as a matrix multiplication, where this inner term here, this entire inner term here, you can call this as some gamma of S2 comma S1. Okay, it is a function of both. See, the moment you sum over U1, there is no dependence on U1. So, there is only a dependence on S2 and S1. So, now you can see that this expression with this entire thing replaced by gamma of S2 S1 looks like a matrix multiplication, and that is precisely what it is. So, I will just spell that out for you. So, then the matrix multiplication will look something like this. You will have F2 of S2 as a result of your computation. So, you will compute F2 of 0 0, F2 of 1 0, F2 of 0 1 and F2 of 1 1, and this is computed by multiplying a matrix with F1 of 0 0, etc. So, this is in general F1 of S1, and this matrix is nothing but your gamma of S2 S1. So, you can so in general you can try to find out what the entries are. In general, the entries, this is where the information from the outside channel, from the Y's actually comes in, but what I want to pay attention to is where you have zeros and where you do not. So, for example, supposing you think about this first entry, the first entry will be non-zero if there is a transition from the 0 0 to the 0 0, and in fact there is. Okay. So, you will have a non-zero entry here. Okay. Then is there a transition from 1 0 to 0 0? Okay. The next entry would correspond to a transition from here to here, and there is none. So, that entry will turn out to be a 0. Then is there a transition from state 0 1 to 0 0? Yes, if the input is 0. Remember, what happens is that if you are in this current state, then the new symbol comes in from the left and pushes out the symbol on the right. So, from 0 1 you can transition to 0 0. From 1 0 you cannot, because the older symbol will remain as a 1. Okay. So, that means that you will have the R, and similarly you will have a 0 here, and that is merely a reflection of this in the trellis. See, in the trellis you can in this section of a trellis you see that you can only come to 0 0 from either 0 0 or 0 1. Next the question is, from where can you come if you are headed towards 1 0? The answer is again 0 0 or 0 1. This is for 1 0. So, the next entry is also similar. You can only come from here or here. So, these entries are 0. Now, you want to know, well, where, if I am going towards 0 1, where can I come from? So, I am going to 0 1, I can either come from 1 0 or 1 1. So, that means in this case the stars are here and the zeros are here, and similarly for the last case you will find that it is similar. So, you can think of this like a transition matrix, and it is going to look like this. So, in fact, what the GDL does is that it gives you a very compact representation of your algorithm, but since you are passing functions, implementing them involves operations, certain operations. In this particular case it is matrix multiplication. Okay. So, all that we did here was actually point out that the forward recursion algorithm that takes you from here to here is really a matrix multiplication corresponding to transfer of information across one section of the trellis. So, in general you can actually see that if your trellis is very long, then you are just going to hop from one section of the trellis and you are going to keep on hopping, and you will be multiplying by a matrix at a time. Okay. The matrix will change from section to section because it is a function of the current received symbol. See, because the next time you encounter something like this, you will be hopping from here. Let us say you continued in the forward direction, you would have f2 of s2 here, and then you would have f3 of s3 here, and then the particular entries would depend upon the local kernel here, which was p of y1 given s1 u1. Here it would be p of y2 given s2 u2. Okay. So, this is what makes the matrix different from section to section, but all said and done it is just a simple matrix multiplication. So, you can actually see that so the forward algorithm is very easily described. Now, there is also the backward algorithm, right. So, you are also going in the backward direction. So, what happens there? So, I think to show that, let me again copy this. And this time let me erase this, because now our interest is in the other part of the algorithm. Okay, so now we want to pay attention to how the algorithm is progressing in the reverse direction. In the reverse direction, the marginalizations, we have to first identify where the marginalizations are taking place, and here it is a little bit different. So, you see that in going from here to here, there is a marginalization over S4. So, here you are summing over S4. Then there is also a marginalization over here, which is a summation over U3. Now, in general, the disadvantage I have in this reverse direction is that I do not have enough states to the left of me to be able to give you the field, but let us just say that in general that there is a function that is incoming. Okay. Let us just say that in a longer trellis I would in general have incoming some function g4 of S4, and what would happen, okay, is that at this point here, after I have marginalized with respect to U3, what I now have is G3 of S3. So, I am going backwards. So, the subscript of the state keeps decreasing. Okay. So, let us write down the expression for this. So, then you have, now this is fictitious in our particular setup, since there are only this many states, there is the function that is coming in, there is no such function. So, we can assume it to be 1, but in general you can imagine that there would be something coming in, because if you elongate this, you would have a repetition of this kind of a thing. So, you would have G4 of S4 coming in, and you would see that your computation would then say that G3 of S3 is the marginalization with respect to you would have the outer one, which is U3, which will have P of Y3 given S3 U3, P of U3, and then the marginalization with respect to S4 of P of S4 given S3 U3, and then you have G4 of S4. So, this then is your recursive computation. Okay, and let me just make a note that in the present case equal to 1 here, but in a larger example it would not. Okay. So, this would be equal to 1. So, this is the nature of the recursive computation, and in fact this is again a matrix multiplication, because you can just, it is just a matter of rewriting it. So, we can rewrite this in the form where you sum over S4 and you have your incoming G4 of S4, and then you sum, you take the sum over U3 inside, and you have P of U3, P of Y3 given S3 U3, and then P of S4 given S3 U3. Okay. So, this would then be your computation, and this entire thing you can think of now as your I have already used gamma, so let me use a different symbol. You can think of this as your delta, matrix delta of S3 comma S4. Okay. So, once again you have G3 of S3 is delta S3 S4 G4, and you see that this is a matrix multiplication. Again, just like was true in the forward case, it turns out that although it looks like you have two terms here, because this is an indicator function, it is going to select only one U3 or nothing. It is going to say that there is no valid term in here, which means that the particular value of this is 0, or it is going to select 1. Okay. So, then you can actually write this down as a matrix multiplication once again, and I am not going to spell that out. So, I will just indicate this on the side here. So, you will have this is equal to this into this, where here you would have G3 of S3, this is delta of S3 comma S4, and this thing here would be G4 of S4, okay, this vector here. So, this would be the form of the recursion in this particular case. So, that is the form. So, the conclusion is that both forward and backward recursions correspond to matrix multiplication. So, the only thing left to actually point out is, well, what is it? So, at this point, once you have computed, so the question is, well, what do you do after that? So, what we have covered thus far is the forward recursion in this direction, which will end up giving you, if you are interested in computing this, it will give you f2 of s2 at this point here, and the backward recursion, which will end up giving you right here g3 of s3. So, you have f2 of s2, g3 of s3, then you have these terms. So, you have that last stretch to go to actually compute u2. So, let us take a closer look at that, and we will stop with that. So, what we know is that coming from this direction you have g2 of s2, f2 of s2, that is what you have here, and here you have g3 of s3. So, the final computation is then you take so there is a further marginalization that is carried out here, and this is a marginalization with respect to S3. So, you take and there is one marginalization here, which is with respect to S2, all right. So, you have that your final objective function, which we wrote out in the beginning. Okay, you are interested in computing here p of uk given y. So, this is your objective function. So, this objective function is now going to be p of u2, that is the local kernel there, times a marginalization over state S2, and the terms involved there are p of y2 given S2 u2, f2 of S2, and then there is a marginalization over S3 of G3 of S3 times P of S3 given S2 U2, and this also can be given a simple interpretation, but we have just 1 minute left. So, let us just quickly summarize. So, I explained in some length maximum likelihood code symbol decoding of the convolutional code, and this is also known in the literature as the BCJR algorithm. We looked at it from the GDL point of view and went in and zoomed in and looked at in detail at exactly what messages are being passed. We will continue next time, and we should be able to wind up our discussion on the GDL next time, and then we will begin talking about LDPC codes. Okay. So, thank you.